If f of x equals x over x plus 2, find f of x and its domain. Here, we're not composing one function with another, we're composing one function with itself. Now, we do still have to look at the domain here. We know that with a rational function like this, we have to make sure that the denominator is not equal to 0. So x plus 2 must not equal 0. And if we subtract 2 from both sides, we can see that x is not allowed to be negative 2. Now that we've done that, let's look at the composition of functions. F of x. Now on the inside, we've got f of x. So this is going to be f of, and then f of x is x over x plus 2. So then we have to evaluate f at the input x over x plus 2. So up here, wherever we see an x, we have to replace it with x over x plus 2. So the numerator here is going to be x over x plus 2. And the denominator is going to be x over x plus 2 plus 2. So x over x plus 2 plus 2. Just really quickly here, in f of x, wherever we see an x, we have to replace it with x over x plus 2. That's what's going on here. Hopefully some of this highlighting is making things a little bit more clearly where certain things are coming from. Now, we have this expression, which represents our composition f of x, and this is a complex fraction. So to simplify it, we need to multiply the top and bottom by the LCD, and the only denominator in these smaller fractions is x plus 2, so that is automatically going to be our LCD. In the top, when we multiply x over x plus 2 times x plus 2, the x plus 2's cancel, and we're just left with x. In the bottom, we're going to have to distribute to both of those terms. When we multiply the first part by x plus 2, the x plus 2's cancel, and we're left with x. Then we have plus 2 times x plus 2. Now, let's go through and simplify the denominator. If we distribute the 2, that's going to be x plus 2x plus 4. And x plus 2x is 3x. So we end up with x over 3x plus 4 as our composition. Now we do have to check the domain. Here, we start with x, and then f takes x as an input and gives x over x plus 2 as an output. And then that goes into f again, and we get x over 3x plus 4 as an output. So let's take a look at the domain. We know that when f acts upon x, f is not allowed to have negative 2 as an input, so we know that the input x cannot be equal to negative 2. For the second function, again, we have f, and we know that the input can't be negative 2, but in this case, the input is x over x plus 2. So that cannot be equal to negative 2. And we need to solve this inequality for x to figure out what the second restriction is going to be on the domain. To solve an equation with fractions in it, we need to multiply both sides by the LCD. In this case, the LCD is x plus 2. On the left-hand side, when we multiply by x plus 2, the x plus 2's cancel, and we're left with x. And then on the right-hand side, when we distribute, we get negative 2x minus 4. Now we've got x's on both sides, so we can add 2x to both sides to get all the x's on the left. This gives us 3x is not equal to negative 4. And to get x alone, we divide by 3. And this tells us that x cannot be equal to negative 4/3. If x is equal to negative 4/3 and we substitute that in here and here, then this whole quantity will be equal to negative 2, and we'll end up with something that's undefined. So our composition of functions, f of x, can be expressed as x over 3x plus 4. However, our domain is going to be the set of x such that x is not equal to negative 2 and x is not equal to negative 4/3. In interval notation, this is going to be the interval from negative infinity to negative 2, union negative 2 to negative 4/3, union negative 4/3 to infinity. And the reason that negative 2 came first before negative 4/3 is because negative 2 is less than negative 4/3. If we were to look on the number line, and I'm just doing a very rough sketch here, negative 2 is right here, and negative 4/3 is the same as negative 1 1/3, so that'll be right there. So our first interval is from negative infinity to negative 2, then negative 2 to negative 4/3, and then negative 4/3 to positive infinity. And so this is our answer. We've got our function, and we've got the domain represented either way.